about timers, and especially timers and PWM, and then, of course, interrupts. Um, okay, let's take a look at first the scoreboard. I updated it. So down here, again, if you don't see your name in here, it means that you have not enrolled to the course yet. So if your name is not here, then then you need to go to the where on this link and give your name and stuff there. That's the only way you can get credits from this course. And then I already started looking at these exercise returns. If there is R, it means that I received your exercise return. And then I also kind of organize so that they'll be in the same blocks, you know, the same blocks for each group, easier to find your name there. And these are on the order of who returned the exercises first. So Michael, Neil, and Michelle actually were the first ones to return this exercise. Yoo-hoo! Good for you. There's absolutely no reward on that one. Okay, but anyway, so the timers. Let's take a quick look. What is this all about? So we will be playing with the servo motor, especially that. I recommend using this SG90, which is 9-gram servo motor, meaning the motor weighs 9 grams. Okay, there are some information you can find for the servo motor on the internet. Actually, I just added a link here, which should take you what was the page name? It was Components 101, which has some generic information about this type of servo motors. So, okay, especially the pin out. There are 3 pins. Usually this size of a servo doesn't do any damage to your electronics or the other way around, even if you connect the wires different way. It just doesn't work. But anyway, the servo is really easy to operate. You just plug in the power and then you control the angle by pulse width modulated pulse, PWM pulse. So period is about 20 milliseconds, and then basically the duty cycle, controlling duty cycle is between 1 and 2 milliseconds. And then it just turns the angle. All of these servos are a little bit different actually. These are the cheapest you can buy, almost the cheapest you can buy. They are something like €1 something from eBay. If you buy 100 of them, they will be less than €1 each. So, but anyways, easy control by pulse width modulated signal. These have been used in radio controllable toys forever, as long as we have had radio controllable toys. That's why they are so cheap. And then what else I should tell you about it? Okay, this actually tells almost everything what you need to know. Basically, servo is a really simple device. It just has a DC motor, some H-bridge driver, of course, it has the decoder for this the signal, and it has also have the position encoder or angle encoder, and this is quite nice since you can see that it also has a gearbox. So you know that the small DC motors usually don't have much of torque, but if you have a gearbox, then it basically works as a torque converter. So it amplifies the torque. And believe or not, but this actually can lift 2.5 kilograms if it's only 1 centimeter away from the axis. So it's quite a lot for this small toy part. And that's why it's also used on these model airplanes or RC cars, steering the wheels, even when it's you have a lot of speed and a lot of torque on those parts. You need something powerful to control those angles. Okay, so that's the device you will be playing with toys. Another part actually is the let's see, let me open the exercise. Was it already? Yes. Okay, so setup task is, let's see, servo and button press and interrupts. Yes, the interrupts part of PSOC. That's an interesting thing, actually. Let me go and start my PSOC designer. There we go. So PSOC designer. Let me open a new project with the same processor, since I need to show you something. And just for fun, I'll show you how to handle the interrupts in PSOC by adding here just a pin. Yesterday I think I used button the port 1.4 for my button, and then I had also the pull down resistor there. Okay, how about if I then also add some interrupt kind of thing? So when I enable one of those three interrupts, I can then actually have an access to interrupt service routines. Okay, so let's see. Falling edge, rising edge, change from breed. Maybe rising edge would be good. Yes. Initial value is 0. It's pulled low, and whenever I push a button, then I want to have an interrupt. Okay. There. So next thing would be to generate all the needed files. Okay, let me open this one a little bit. So currently the project has the source file. The only source file is main.c. Then it also has this device dependent H files, header files, which are part of the package. This will be there whenever you start a new project. When I click the generate configuration file, that actually generates you the boot.asm and then adds also the library functionalities. Okay, those are the library source files are assembly code, and library header files are these the header for C programs and also those. Okay, yesterday we already noticed that that PSOC GPIO int actually have these definitions, mnemonics to handle the whatever you need to handle there. Okay, and there's absolutely nothing more. Let me close that. Okay. Let's take a closer look at boot.asm. So boot code. So this is the code which will be located at the beginning of the this flash memory. Boot code. Okay. Since this has the interrupt vector table, meaning the jump locations for all interrupts. The first interrupt vector is always the reset interrupt, meaning that okay, everything starts over. Okay. So, and on that one there is only jump to start, and that start is somewhere on the bottom of this file. I'm not interested about that one. There are also the other interrupts like low voltage detection interrupt, and basically what there is, it just halts the processor, since if you have too low voltage you don't want any damage to the circuits. Low voltage actually damages the circuits more than high voltage, especially the flash. You can brown out your flash if you start accessing the flash memory with a too low voltage, meaning that then you can throw the device away. That's why low voltage detection is fixed with the halt command. Okay, but yes, you can actually go and mess up this thing, but it needs active messing up. All right, so since this is just code, you can edit the file. Definitely you can just, But anyways, then there's interesting section. These are the different blocks are giving the next section for the interrupts. And basically there is, well, that's commented out. But basically there are these calls to handling routines. And these actually come from the analog column 0, 1, 2, 3, meaning these interrupts are coming from this part of the device. So basically that first interrupt there, which was called 08. If you had an interrupting logical device in this first analog column, then it would actually had interrupt service code here, or call to your interrupt routine here. Another thing to notice here, that always when you have an interrupt, you have to return from interrupt using red I, not the return. This is one way of handling the interrupts. You have a call of a subroutine, the normal call to a normal subroutine, and then basically after exiting that normal subroutine, it comes here, and then it has a return from interrupt, meaning the popping out the the code location where it was interrupted from the stack. Okay. Yeah, and so on. Okay. Here we go. That's what happened to this boot table when I actually allowed this pin to have a rising edge interrupt. So when a rising edge interrupt happens here, meaning I push the button, the code actually starts here. at this location 1C, which is GPIO interrupt vector, and there is just long jump to SOC GPIO interrupt service routine. And this, I can say already that this routine must actually be somewhere on those assembly files. Why is that? Because there's no underscore here. Have you been playing with the C and assembly code with some microcontroller? Okay, now you will. So C compiler basically makes a pseudo assembly code. Pseudo meaning that, okay, it's mostly assembly, but there are some specific things there. How usually, this is quite usual way of separating assembly code routines or mnemonics from C code mnemonics. Assembly code basically is just, mnemonics are just like that. But if you have a C routine, and on C routine, for example, main, okay, here I have only main function. This looks like in assembly code as underscore main. So whatever mnemonic you have on C code, you just add underscore and you can call that routine from assembly code. Okay. There are different ways of calling assembly code from C, but I'm not going to that. I just hope that you don't need that. Okay, but anyway, somewhere there should be SOC GPIO interrupt service routine, and my guess is that it's here. SOC GPIO int.asm. Whoa. Yes, that file has the interrupt service routine. Yep. You know what export means? Yeah, it said yes. So basically it just tells the linker that, okay, this is linkable with the other routines from the different files. Okay. Export. There are some sections you can actually edit. For example, here, if you have some assembly declarations here, you would put them here. Insert your custom declaration below this banner and above this banner. Usually you don't have anything. This part is the most important part. That's the actual code that will be executed when interrupt happens. And let's take a look at the boot. Okay, yes. So there's a long jump to this routine or this section of the code. This is just code section. So it just continues from this point. Yep. Okay, what is the difference between jump, long jump, call, and long call? Remember those from microcontroller classes, microcontroller programming. So if there is a long jump, as I had here, it just jumps into code section. There is no subroutine actually here. Absolutely no subroutine. So this is just a code section. If there is a call, like in these actually, then there is an actual function there which will be called. Okay. The difference basically is that if you want to really encapsulate your local parameters, you probably want to use function. Otherwise, in the interrupt service routines, it does not make much difference. Okay, so what else? And which means that basically this interrupt service routine stops with the return from interrupt code. So basically, it does not actually come back here. So it's a long jump, it cannot come back. Yeah, so it just continues the execution here, which means that we have to have the return from interrupt on this code section. Good. Okay, and that's a perfect place to put your own code. And since this is, again, we are not practicing building IKEA furniture, which needs a lot of assembly. Oh boy. Yeah. We basically just need a one single line here to call a function which is actually written in C. And let's see. Now I need to take a closer look at the. Oops. Oh, wow. Now I need to take a closer look at my interrupt thingy here. Depend tricks. I need to find the call path. Can I find it here? I can always just guesstimate it. Long jump, not long jump. Why I don't find it? Okay, maybe we do it that way. Okay, in this code you can actually then have both the ways, either long jump or long call. Okay, why long? The difference between long jump and a jump is basically the distance or in bytes of those code sections. So if that the routine that you are calling is on a different page, meaning on different block of 256 bytes, you need to use long jump. Then it will be 2-byte long address. Jump address is always just 1 byte, so the code must be on the same page. Okay, but long jump can jump into the 16-bit address. Since we are not sure how squeeze the memory locations on the beginning of this code is, we use long jump instead. Okay. If we are actually doing long jump, then we need to have the routine that it jumps to have the return from interrupts. Otherwise, the stack will be broken. If the other way is actually to have a long call to your routine, then it returns back here, back into this point, and then there is the return from interrupt. But say more cost efficient would be to have long jump. Long jump to your routine. For example, my interrupt service routine. And okay, by adding the underscore character there, basically, let me take a quick look. Yeah. Underscore character here. Then that states that this code actually can be found from some C file or precompiled C file. Okay. That's the only thing you need to do in this routine. Well, maybe you want to save it. Okay, and next thing would be to go, for example, into main.c and add your code there. Or you can actually create a new file which has the interrupt service code there. If you have a big project, then you probably want to have this code separately on different file. But anyways, that's more like a software engineering than embedded engineering. So this is my way. So, okay, I will write my ISR code here. And basically, it's the interrupt service routines always are type of void. And then the function itself. And how to tell this one that this is an interrupt service routine. That actually is stated on the in here. You will have a pragma interrupt service routine. So pragma interrupt handler. That states that okay, next function is actually a function where you return from interrupt. There we go. That's all the hooks you need to do in order to then write C code instead of assembly code. So whatever you put here will be executed in case of button press. Except, of course, at some point you have to enable the global interrupts. And I think you also need to enable the GPIO interrupt somewhere. Timer. Let's see, sources. Interrupt service table. First priority. Yada yada blah blah blah. Does it have any? Oh, there, yeah. You need to also have that line there. So enable global interrupt is just enabling the interrupt service mechanism. And then in addition to that, you need to also enable the enable also the GPIO interrupt. Okay. So practically now everything is done for this interrupt service. Those small tricks. So, okay. So let's take again just a review of how the mechanism actually goes. So if you want to have a pin interrupt, you need to actually give a pin A. name, and then also the saying which interrupt it should use. So this is the rising edge interrupt on pin 1.4. Okay, and I renamed that as a button. There we go. And when you click the generate the header files, then basically what it does for you, it generates the boot table, and on boot table you would have where is that GPIO 1C. Okay, so this actually comes from the development tool. Yes. Yes, I will. Yeah, I'm repeating everything. Oh, this one. Okay. So I just renamed a button, put the pull down drive, and then give a rising edge interrupt. Rising edge interrupt, and then generate the configuration files. Will give you this line on these 3 lines on this boot.asm. Boot.asm is actually the code that starts the whole thing. That's a boot code. All right. So basically, here's just a long jump to SOC GPIO-ISR. Okay. So it jumps into this routine right here. SOC GPIO-ISR, which can be found from SOC GPIO in .asm. Okay. And here I have just a redirection, again a long jump to my own interrupt service routine, which is written in C and which is currently empty. Okay, so just a long jump. You need to put it in between of this section. There's insert your custom code below this banner and insert your custom code above this banner. So that's why it's right. You must put it right there, is that when you click the generate configuration files, the system goes and checks if there is anything there. It doesn't touch that part. Okay, that's nice. You don't need to add your code every single time you press the button. All right, so there's just a long jump, and basically it's a long jump, and then you need to write your own code somewhere. In this case, I just put it in main.c at the end. So this pragma statement here actually tells the compiler that, okay, this is interrupt handler type of routine, meaning that it will compile this one and add return from interrupt at the end of the code. Okay, that means that you don't need to do everything in assembly. And then whatever you put there will be executed. Okay, some ID. Yes, you have a question. Yeah, here. It's, yep. Okay, let me come on to, so you have a pin, and you rename that pin, right? It doesn't matter what you use the name. Yeah, and then, but anyways, the rising edge interrupt. Yeah. When you have the rising edge interrupt there, then after that one you click generate the configuration files. Then you should get the 1C. You should have this line on the boot code. And on sock GPIO in.asm, you will edit this one yourself. Okay, and then you go to the main file and add pragma and the routine. Okay. Then how to handle these interrupt services? Usually the good idea is basically to have as little as possible done inside of the interrupt service routine, because the interrupt service routine can be also interrupted by higher priority interrupt. And if you have any global variables inside of those interrupt service routines, it means that you might actually get the value changing because of the higher level interrupt is changing that one to at the middle of what you are doing there. Okay, so it sounds like not a good idea to put a lot of things to the interrupt service routine. So as little as possible. Small is beautiful, but big is better. Right. I know. Okay, this is how I do usually things. I take the global variables. You know that when you're doing, say, normal programming, you should avoid global variables. But this is embedded coding. You cannot avoid global variables. You cannot. So you just should avoid them, but in some places you just must use them. For example, you can have global variables and use them as the mutexes, mutual exclusions, or then the what is the other one? Well, tokens, kind of tokens, flags. So, for example, I could have a kind of button pressed variable. Oops, not it. And on the beginning, I just give it initial value 0. So this is the flag to indicate if the button is pressed. All right. And on that interrupt service routine, I would just have button pressed equals to 1 or plus plus. This would give you more information. For example, was there more than one button press? But, well, it's up to you to decide if you want to kind of avoid multiple button presses. Since basically if you have a mechanical switch, you usually get more than one rising edge, since that's this bouncing. Okay, so this is now exactly how I would like to see those interrupt service routines. This is you just do whatever is needed and not more than that, as little as possible. You just indicate, okay, button is pressed, and you will do the real code then inside of the main routine, or have a different routine to do the whatever calculus you need to do there. Okay, so for example, in here you have that while one loop, and inside of the while one loop you would have, okay, for example, if button button pressed then do something. Maybe I should actually move that one here. There. For example, a display routine showing something on the display. Okay, so that's the general idea how to make the interrupt service routines working. So it's quite straightforward thing, but yes, there are several places you can go wrong. Okay, so let's see. First of all, you need to have the interrupt source. In this case, it was a button interrupt. But on the other hand, in this exercise, there are basically PWM. You can also have the PWM module to give you the interrupt. And there's the interrupt type, terminal count or compare true. Usually terminal count. Okay, so, and of course, now if I press the this one here, I will get PWM8 interrupt code here. And similarly on boot.asm, I have the digital block interrupt. Ooh, that's nice. Long jump to here, so I guess it's right there. Okay. Yep. So you need to again make your own code, and yes. Well, it's up to you. It's your code. Okay, let's see. What is the difference between terminal count interrupt and compare true interrupt? Yes, there is a difference. One way to find out the difference is take a look at the datasheet. Datasheet. On the right corner, there's supposed to be a datasheet. But practically, those interrupts actually are, well, pulse width modulation module actually will give you period counts. It's a full period. If you have a compare true, no, that's a terminal count. Terminal count interrupt actually happens here. Compare true interrupt happens here. Yeah. So it's up to you to decide. You're the software engineer here, embedded software engineer, which makes more sense. There is actually a one hint. This reloads during the terminal count. So if you want to adjust the next pulse width by interrupt service routine, you probably want to have this reload value ready right after this compare true. So interrupt here, then you would have some time to basically change the reload value, and when this PWM runs to the end, then it basically reloads the new value. Okay. But anyways, so let's take one more time, since interrupts are the most important part of this the embedded systems engineering overall, at least in my point of view. Okay, my primary interrupt source was the button press, and pull down just means that there's a pull down resistor here. So you can add a switch, external switch, no more different components. Rising edge interrupt means when I press the button, the interrupt happens right there. Okay. The code, by clicking the generate configuration file, will give you actually boot table. And 1C was the GPIO interrupt, and there's just a long jump to the GPIO interrupt service routine. Good. And that one actually then is jumping on this code section here. GPIO interrupt service routine. And again, there's a place you need to put your own redirection code. Long jump to underscore my ISR would be jumping into your code in C with the name my ISR. This is just a normal function, or basically, well, it's defined as a function, but the compiler will just make it a code section named underscore my ISR. Because I have this pragma interrupt handler here. So that defines that this code section will be ending with return from interrupt. Okay, that's one way of doing it. On that PWM interrupt, or do you have any questions on this one? Yeah. So yeah, and one more thing is that do as little as possible on the interrupt service routine, since the interrupt service routine can be easily interrupted by higher priority interrupt. Okay. So just flags or simple things like the increment of a variable. That takes about three. Yes, it takes about three assembly commands. One is to read a variable. Another one, well, read a variable to register, then increment register, and then write back to that variable. So three commands in the assembly code. Takes about, not too many times. I think it's about 5 microseconds in this. It's pretty good. All right. And there you basically, you need these global variables. Don't be afraid of using them. Okay. Let's take a closer look at the PWM stuff. I added here 8-bit PWM and module. Actually, for the exercise, when you take a closer look at the exercise, I'm asking you to smoothly vary this PWM duty cycle so that basically it doesn't jump into the next angle, but rather go, smoothly that transition. So basically how to do that smooth transition is that you would have an interrupt service routine for that PWM that would increment slowly this the reload value until it hits the desired reload value. Okay, and you can get the smooth operation only by basically having enough of bits, of course. If you have 8 bits, you have only 256, divisions there. And the servo, that's 20 milliseconds. And this here is from 1 to 2 milliseconds. So you have only about 20, or actually, no, about 10 time steps or these angle steps for the full control of 180 degrees. So that's not smooth. Okay. However, how to do the calculations for this? So first of all, I will be showing the exercise using 8 bits, but just a reminder, you need to basically, on the exercise itself, you need to use 16 bits at least. Okay, 16 bits. But anyways, the calculations are exactly the same. So 20 milliseconds, full period. So basically, 8 bits, 20 milliseconds could be, for example, 200 clock cycles. That's less than 256. So it fits into 8 bits. Right. Eight bits. Okay, good. So that actually now defines my clock rate. Yes, 20 milliseconds divided by 200, so one clock should be 0.1 millisecond. Period, clock period, which means that you should have 100 kilohertz. No, not 100 kilos. Is it 100 kilohertz? Not 10 kilohertz. 10 kilohertz clock. How to get 10 kilohertz clock? Okay, we need to have 10 kilohertz clock. Then I could actually put the 200 as my base period. So period 200 and say initial pulse width, say 15 would be between 1 and 2 milliseconds. So that would be, I'll say 15 counts is 1.5 milliseconds. That should put the control at the middle. Okay. Another bits and pieces on this module would be compare type. Less than means that it runs for 200 clocks, not 201. Oh, wait a minute. No, actually, pulse width would be that 15 pulses 0 to 14, not 0 to 15. Okay, so less than. Interrupt, I already have terminal count, and then, well, clock sync. Since we don't have the clock sync yet, clock yet, we basically, let's leave it for a while. That parameter there, now actually, it says clock. Clock sources. You can use something like 10 different sources for clock. Wow. Okay. There's a broadcast clock for the full row. Now it doesn't sound good. The system clock multiplied by 2. System clock is 24 megahertz, and this could be actually 48 megahertz clock running this block. Not good. It's quite far away from 10 kilohertz. Then there's this VC1, VC2, VC3. Okay, that's nice. We actually have the system clock dividers. So let me select, for example, VC2. I think we can do it with that. So the system clock dividers VC1 on the top, on the global resources. We can actually divide the system clock, not the CPU clock, but the system clock. System clock by 2 4-bit dividers and then there's actually one 8-bit divider after that one. So from 24 megahertz to 10 kilohertz. Okay, the divider should be how much? 2,400. Right. Is it correct? No. Kilo mega 24 megahertz. Yeah, that's correct. The divider should be 2,400. Sounds like we need to actually use 3 different dividers. So yeah. Okay. One way of actually doing it would be to divide it by 12, and then 200, and 200 can be arranged by, for example, 2 and 100. Doesn't make much difference. 2 times 100. Okay. So first divider would be VC1 divider is 12. Then the second divider is actually VC1 divided by the number, for example, 2. And then VC3 can have different sources for the division, but the default is VC2. And the divider here is 100. There. Okay, so these parameters, VC1 sysclock divided by 12, then VC2 sysclock divided by 2, VC3 is system VC2 divided by 100. Okay, that gives me 2,400 as a divider for the 24 megahertz clock, and yes, that gives me 10 kilohertz. Okay, when you are doing that 16-bit system, you need to do the calculations over, of course. Life is not easy. Haha. At least not on my class. All right, so now I have the correct dividers, and then the clock would be, in my case, in this case, is VC3. Yeah, you need binoculars to see those parameters. Sorry about that. Okay, enable. Okay, enable. There's some mentioning about enable in datasheet. Let's take a quick look on the parameters. A high input enables continuous count, while a low enable disables count with resetting the counter. So I would guess that we set the enable high. So that is continuous counting. It also, you can have hardware also defining that if it's on or off. And then read the documents carefully about the parameters, since sometimes you have to set it something else. Everything is in this documentation. Compare out. Okay, now we are starting to get there. How to get this data from that block to some pin. Wow. Alrighty. PWM8. Enable is high. Clock source is given. Compare out. Must be actually now routed to some pin here. I'll show it the reverse way. I like actually doing things on finding first the pin and then figuring out where I can connect. But anyways, the idea is that on left, these green lines are basically the input input lines for odd ports and even ports, and on the right hand side the green lines are the output lines for odd ports and even ports. So if I, for example, take the port 1.2 and select where the signal comes from, you can actually, if this is the output port, you should actually select the global output odd 2. That is the only line I can connect it here. Another thing, drive strong, because we are actually driving outputs. Interrupt, well, we already have interrupting from the block itself. We don't need the pin interrupt in addition. No interrupt for this pin. There we go. Magically, we have now connection between that line and that port. That's the only way you can get outputs of the block to any of those pins. Okay, let's see. On that, how to connect this one in here. Basically, there's only the selection of connecting this line to pin port 1.3 or nothing. Interconnect actually means that we can connect either output to input or directly from input to output, but that doesn't help us either. So basically what we need to do is to take one of these lines and connect it in this the output line, and that's basically the row output lines here, and those are those you can select where the output goes from this box here, and guess what? Row output 0. Row 0 output 0 can be connected only on those 4 lines by enabling the buffer. So line 0, 4, 0, 4. Okay, not good for us. I want to connect to global output odd 2, so actually I can do it from here. So that connects to global output odd 2. There we go. Now I have this line connected to that, which is connected to port. Okay. And now basically I can connect this compare out, which is the pulse width modulated signal, to row 0 output 2. There. It's a little bit, complicated thing to do, but anyways, that's how you do it. So first you find the pin where you want to put that one, start routing backwards until you find the block. Row. That row. Okay. If you click that icon here, it gives you the buffers. And then you basically just turn on the buffer. By the way, you can turn more than one buffer. So if you want more than one, exactly the same signals, you use them probably somewhere else. Then you can have multiple lines there. There. And then it's 1.2. So generate configuration files. Okay, reload, reload, reload. And modify the main file, modify the interrupt service routines, that kind of stuff. But anyways, let me PWM8 start. Okay, maybe I want to have the data sheet, application programming interface, or code sample might actually work better. Start, okay. Just start, and then maybe, yeah, so this code here should then put this server at the middle position. They are also, as you can see from the datasheet code sample, then you can access the pulse period and pulse width by some API functions. Okay. On the left corner, they should have it here. Okay, when you have the main open datasheet on there. Okay, in that case, basically go to chip level again. Click on PWM8 module. On this view, you have datasheet on the right-hand side, but on the main.c, you should have the datasheet on the left-hand side. If they are not there, you could actually take a look at the view and there have the datasheet window turned on, if it's not on yet. Okay, yeah. All right, so this simple code now should start the, well, GPIO interrupts and put the PWM start there. Maybe I can actually now modify also the, okay, not that one. Modify, for example, pulse width. If button is pressed, I will change the pulse width was 15, so let's move it to other end, 10, for example, just to see if this system works. Notice that I haven't enabled the PWM8 interrupts yet. You would do it on the exercise in order to get the smooth transitions. All right, let's see what happens if I compile everything. Whoa, what happens? Actually, no errors. This doesn't happen every day. Okay, there we go. Program path. Reset mode, power on. Why it doesn't? Fail. I see. This programmer pod connector is actually getting loose. I think you need to twiddle them if it doesn't start programming immediately. All right. Fail. Why did it fail? Pass. Good. Yep. Okay. There are two types of servos here. Use the smaller one because basically this doesn't draw more than 100 milliamps of power, meaning that you can plug it into this the development board directly. If you use higher power servos, then you probably need to have external power supply, which we don't have. Okay, so with some luck, I should have the system ready and button press should let's see. When you're making the connections to the development board, remember to turn off the power when you are doing those. Especially now when we are actually taking some power off the board itself. So the connections, let's see, I had the connections somewhere. Yep, connections. Brown is ground. And the red is plus 5 volts, and then we have a port. Which did I use? Hmm. 1.2. All right, programmer part. Okay, let's see. Does it work or not? Button press. Why nothing happened? Strange. Okay, so any questions? Lots. All right, but anyways, that's the way you can control a PWM and how to have interrupts. On your exercise, the PWM interrupt code is a little bit different from the GPIO interrupt code. Let's take a quick look. First of all, on the boot.asm, we don't have the long jump, I think. We have... Oh, it has long jump. Okay, good. So block DBB00 interrupted vector. So this is not different at all. In this code, that's another way of calling a function from interrupt service routine. I like the way we did the button press interrupt better. So this is a normal call to the function. Okay, with this way, you do not need to actually do other than just get rid of that one and then write your own C function on main file. Okay, there. Yeah, that will be enough. You don't need to have the pragma. On the other hand, this would then return back to this code separately. Okay, and basically you would like to have also those. That's basically putting most important registers to stack, just in case. But if you are using the long call, then you must actually return here and restore. So this is the pulling these register values back. But if you're doing it the other way around with a jump, you could have this one also like this long jump underscore that one. But then on the main.c, you must also have the pragma interrupt handler like that. Otherwise, your code actually corrupts the stack pretty fast. There's only a couple of hundred bytes in the stack. Okay, so either of those methods. So if you don't have the pragmas here, then you must have the long jump, long call. And when calling a routine, you also might also have those macros like preserve CPU content and after that restore CPU context. But still the same thing, you do as little as possible on the interrupt service routine itself. Yes. In boot ASM, it's just a long jump. Yeah, once it's called once every interrupt. Yes. Yeah, every time it interrupts, it actually does that. In this system, you do not need to clear the interrupt separately. It's enough that it goes into this. Yeah, I know. In our processors, I think you need to clear the individual interrupt. Oops, one thing more. I started to think why my system didn't do it as I wanted. Well, this button pressed was a flag. You need to clear your own software flag, of course. Sorry, I didn't remember that one. Button pressed equal to 0. So clear your own soft flags. Now it can be used again. Okay. So that's the example, which might work. And on the interrupt overall, what you need to do, you need to actually enable to global interrupts if you have any interrupts at all. Then you need to also enable that particular interrupt. On PWM, you can enable to interrupt by, okay, on the application programming interrupt, I think there's a sample firmware, read counter, pause with, write period, start, stop, enable int, okay, there. PWM8 enable interrupts. If you want to have PWM8 interrupts working. There. Small things. So first, define the interrupt on the chip design. The sources for interrupts are defined here. Generate application, generate the configuration files actually will create you the code where to put your own hook for the C routines. Two different ways of doing it on the this SOC GPIO interrupt service routine. Just a long jump to my ISR, and then you must on your C code you must have the pragma. If you have a long jump, then you use pragma interrupt handler and define that one as a interrupt handling routine. The other way around is how it's done on the that PWM interrupt is to have a long call to your routine. And then you do not have the pragma. The difference is that after this code, it has the return from interrupt. So it goes back to where it was, whatever it was doing after that one. In here, this one returns back to this code. Okay. Yeah. So basically, after this one, it will come here, restore CPU context, and then there's a return from interrupt. Yep, it's hard. All right, so now, good luck for today's exercise. You will need it. The same way as yesterday, I will be here until around 4 o'clock. So I will probably go to have a lunch around 1 o'clock. So, but anyways, start working. If you have any questions, ask anytime. Good.